Albert Einstein, a name synonymous with genius, left an indelible mark on the world with his groundbreaking theories of relativity. Yet, even Einstein, with his unparalleled intellect, couldn't escape the allure of an unsolved puzzle that would consume the latter part of his life. This enigma, the unification of physics, remains a tantalizing challenge for physicists today. Einstein, a maestro of physics, yearned to weave these disparate movements into a unified symphony, a single, elegant theory that would encapsulate the universe's grand design from the smallest particles to the largest galaxies. This quest for unification, this elusive theory of everything, became his holy grail, a pursuit that would both illuminate and frustrate his later years. Imagine the universe as a vast cosmic tapestry, woven from the threads of fundamental forces and particles. He believed that beneath the apparent complexity of the cosmos lay a hidden simplicity, an elegant set of principles that could explain it all. The more he delved into the depths of general relativity and quantum mechanics, the more he realized the profound chasm that separated them. General relativity, Einstein's crowning achievement, unveiled a revolutionary perspective on gravity. Imagine a trampoline, its surface representing the fabric of spacetime. Now picture a bowling ball placed at its center. The ball's weight causes the trampoline to sag, creating a curvature around it. Massive objects, like stars and planets, warp the fabric of spacetime, and it's this curvature that dictates the motion of objects within their gravitational influence. Einstein showed us that gravity is not a force at all, but a consequence of the geometry of spacetime itself. General relativity's predictions, often bizarre and counterintuitive, have been spectacularly confirmed by observations. The discovery of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects, further solidified general relativity's place as a cornerstone of modern physics. Now let's journey into the heart of matter, into a realm where the familiar laws of physics seemingly dissolve into a haze of probabilities and uncertainties. This is the quantum realm, the domain of atoms and subatomic particles, where energy, momentum, and other physical quantities are no longer continuous but exist in discrete quantized packets. In this strange realm, particles can be in multiple states at once, their fate determined by a roll of the quantum dice. Imagine a coin spinning in the air, never landing on heads or tails, but existing in a blurry state of both possibilities simultaneously. This is the essence of superposition, a fundamental concept in quantum mechanics. It's only upon measurement that the wave function, the mathematical description of a particle's quantum state, collapses, forcing the particle to choose one state or another. Then there's entanglement, a phenomenon so bizarre Einstein himself dubbed it spooky action at a distance. Quantum mechanics, despite its weirdness, has proven to be incredibly successful in explaining the behavior of the microscopic world. Here's the rub: general relativity, the grand symphony of the cosmos, and quantum mechanics, the intricate ballet of the subatomic world, refuse to dance to the same tune. At the heart of this incompatibility lies the nature of space and time. General relativity views spacetime as a smooth, continuous fabric, warped by the presence of mass and energy. Quantum mechanics, on the other hand, suggests that at the smallest scales, spacetime is not smooth at all, but rather a turbulent sea of quantum fluctuations. These cosmic realms, where gravity is incredibly strong and quantum effects dominate, become battlegrounds for these two titans of physics. In the intense gravitational fields of black holes, general relativity predicts a point of infinite density, a singularity where the laws of physics as we know them cease to exist. Quantum mechanics, however, abhors infinities, suggesting that something else must happen at such extreme scales. Without a unified theory, our picture of the cosmos remains fragmented, a jigsaw puzzle with crucial pieces missing. The quest for a unified theory, for a single framework that can reconcile the seemingly incompatible worlds of general relativity and quantum mechanics, has become the holy grail of modern physics. Physicists today, much like Einstein in his later years, are tirelessly exploring new avenues, venturing into uncharted territories of theoretical physics. Among these ventures, string theory and loop quantum gravity stand out as the most promising contenders. Imagine the universe not as we perceive it but composed of tiny vibrating strings, far smaller than the smallest subatomic particles. This is the radical proposition of string theory. Loop quantum gravity, on the other hand, takes a different approach, focusing on the quantization of spacetime itself. These loops at the Planck scale, the smallest possible unit of space, represent the fundamental building blocks of spacetime. The road to a theory of everything is fraught with challenges, but the pursuit continues, driven by an insatiable curiosity. Our journey into the depths of Einstein's universe begins with a simple yet profound shift in perspective. Imagine, if you will, a universe not governed by invisible forces acting at a distance but rather by the very fabric of spacetime itself. This fabric, far from being a static backdrop, is a dynamic entity capable of bending, warping, and rippling under the influence of mass and energy. To grasp this concept, let's envision a trampoline stretched taut, its surface representing the fabric of spacetime. Now, picture placing a bowling ball at the center of the trampoline. What happens? The ball's weight causes the trampoline to sag, creating a curvature around it. Just as a marble rolling on the trampoline would naturally follow the curvature created by the bowling ball, objects in the universe travel along the contours of spacetime, warped by massive objects. Gravity, in this context, ceases to be a mysterious force acting at a distance and instead becomes an emergent property of spacetime's geometry. To truly appreciate the elegance of general relativity, we need to understand the stark contrast between Newton's and Einstein's views of gravity. In Newton's universe, gravity was an invisible force that acted instantaneously across vast distances. An apple falls from a tree because the Earth exerts a gravitational force on it, pulling it towards its center. The Moon orbits the Earth because of the Earth's gravitational pull. While Newton's law of universal gravitation worked remarkably well, it couldn't explain some subtle gravitational effects. Enter Einstein and his theory of general relativity. Einstein proposed that gravity is a manifestation of the curvature of spacetime itself. Massive objects like stars and planets warp the fabric of spacetime around them, much like the bowling ball on the trampoline. General relativity, for all its theoretical elegance, needed observational evidence to solidify its place in the annals of science. And evidence it found in one of the most spectacular displays of scientific prediction and confirmation in history: the bending of starlight during a solar eclipse. According to general relativity, the sun's massive presence should warp the fabric of spacetime around it. This warping, in turn, should deflect the path of starlight passing close to the sun, causing the apparent positions of stars to shift slightly. Enter the solar eclipse, a celestial alignment where the moon passes between the Earth and the sun, momentarily blocking out the sun's light. In 1919, during a total solar eclipse, British astronomer Arthur Eddington led an expedition to observe this very phenomenon. The results were groundbreaking. Eddington's observations showed that the positions of stars near the sun's limb were indeed shifted, precisely as predicted by general relativity. Einstein's symphony of spacetime wasn't done revealing its secrets. General relativity predicted another mind-boggling phenomenon: gravitational waves. These waves are not like the light waves we see or the sound waves we hear, but rather ripples in the very fabric of spacetime itself, generated by the acceleration of massive objects. Imagine two black holes locked in a cosmic dance, spiraling towards each other at incredible speeds. As they dance, they warp and distort the spacetime around them, sending out ripples like waves spreading from a stone dropped in a pond. These ripples, these gravitational waves, carry energy and information about the cataclysmic events that created them, propagating outwards at the speed of light, stretching and squeezing spacetime as they travel. Detecting these elusive waves, however, proved to be a monumental task, a testament to human ingenuity and scientific collaboration. It wasn't until 2015, a century after Einstein first predicted their existence, that the elusive whispers of gravity were finally heard. Using incredibly sensitive instruments called laser interferometers, the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting the first gravitational waves emanating from the collision of two massive black holes billions of light-years away. This momentous discovery, a triumph of experimental physics, opened a new window into the universe, allowing us to listen to the cosmic symphony of merging black holes, colliding neutron stars, and other cataclysmic events that had, until then, remained hidden from our view. General relativity's impact extends far beyond the realm of black holes and gravitational waves. It provided the very foundation for our modern understanding of the universe's evolution, leading to the development of the Big Bang theory, the prevailing model for the universe's origin. Einstein's equations, applied to the cosmos as a whole, painted a picture of a universe that was not static and unchanging but rather dynamic and evolving. In the 1920s, Belgian astronomer Georges Lemaitre, drawing upon the implications of general relativity, proposed that the universe originated from an extremely hot, dense state, and had been expanding ever since. This idea, initially met with skepticism, gained traction with Edwin Hubble's groundbreaking observations in the late 1920s, which showed that galaxies were indeed moving away from each other, and the farther away they were, the faster they seemed to be receding. The expanding universe, a concept that emerged from the depths of general relativity, became a cornerstone of modern cosmology. It suggested that the universe had a beginning, a moment of creation now known as the Big Bang. It also implied that the universe's fate, its ultimate destiny, was intimately tied to the dance of gravity, to the interplay between the expansion driven by the Big Bang and the gravitational pull of matter and energy within it. General relativity, in a sense, gave birth to the field of cosmology, providing the theoretical framework for understanding the universe's origin, evolution, and ultimate fate. It revealed a universe far more dynamic and fascinating than anyone had ever imagined, a universe where space and time were not mere backdrops but active participants in the cosmic drama. Hold on to your hats, folks, because we're diving into the quantum realm, where the familiar laws of physics take a back seat to the bizarre and counterintuitive. In the quantum world, things get fuzzy, uncertain, and downright weird. Particles can be in multiple states at once, and observation influences the observed. This is the mind-bending reality of superposition and entanglement. Let's delve into the heart of quantum weirdness with superposition, a concept fundamental to understanding the quantum world. Imagine a coin spinning, existing in a blurry state of both heads and tails. That's superposition, where a quantum particle can exist in multiple states at once. Forget the clear-cut logic of the classical world. In the quantum realm, it's all about possibilities coexisting in a hazy state. Like a cosmic game show, the quantum particle exists in all possible outcomes until observed. Observation forces it to collapse into a single state. It's as if observation conjures a specific outcome from the quantum hat. Hold on tight because we're about to venture into the realm of quantum entanglement, a phenomenon so bizarre, so counterintuitive, that even Einstein himself famously dubbed it spooky action at a distance. Imagine two particles separated by vast distances, yet linked in such a way that the act of measuring one instantaneously influences the state of the other. That's entanglement, a quantum connection that defies our classical notions of space and time. Entanglement isn't just a theoretical curiosity, it has the potential to revolutionize fields like quantum computing and communication. Entanglement, with its spooky action at a distance, holds the key to unlocking technological marvels, paving the way for a future where the boundaries of the possible are redrawn by quantum mechanics. Section 4. The Quantum Toolbox. From lasers to transistors. Quantum mechanics isn't just an abstract theory, it's the foundation of modern technology, guiding electrons in our smartphones, photons in our lasers, and bits in our computers. From the mundane to the extraordinary, quantum mechanics powers our technological world. Lasers owe their existence to quantum mechanics. They generate focused beams of coherent light through stimulated emission. Transistors, the workhorses of modern electronics, control electricity flow in our devices. They rely on the quantum behavior of electrons in semiconductors. Heisenberg's uncertainty, embracing the unknown. In the quantum realm, certainty is an illusion. Heisenberg's uncertainty principle tells us there are limits to what we can know about a particle's properties. It's an inherent fuzziness in reality itself. Imagine pinpointing the exact location and speed of a blurry, fast-moving object. The more precisely you measure its position, the less certain you become about its momentum. This isn't a limitation of our devices, it's a fundamental principle. Measuring one property disturbs the other, introducing unavoidable uncertainty. This uncertainty reflects the wave-particle duality of matter. Particles behave like waves described by probabilities. The uncertainty principle limits how well we can pin down a particle's wave-like nature. Embracing uncertainty is a profound implication of quantum mechanics. It challenges our classical intuitions, forcing us to embrace a probabilistic reality. The future is a tapestry of possibilities, each with its own probability. When gravity and quantum mechanics collide, picture this: two heavyweight champs in the ring. General relativity, king of the cosmos. Quantum mechanics, ruler of the subatomic world. What happens when they clash? Chaos. Relativity thrives in the macroscopic world. Quantum mechanics governs the microscopic. They can't agree on space-time. Relativity sees it as smooth. Quantum mechanics sees chaos. This clash puzzles physicists at extreme scales. Let's get down and dirty with this space-time squabble. General relativity describes gravity as the curvature of space-time. Think of it like a bowling ball on a trampoline. But zoom into the Planck scale and things get messy. Quantum mechanics tells us the vacuum of space isn't empty. It's teeming with virtual particles like subatomic fireflies. These particles borrow energy and disappear. Defining space-time curvature here is like measuring waves on a stormy sea. This conflict lies at the heart of modern physics. Black holes, those enigmatic cosmic beasts, are where the battle between general relativity and quantum mechanics reaches a fever pitch. These gravitational behemoths, formed from the collapse of massive stars, possess a gravitational pull so intense that nothing, not even light, can escape their clutches once it crosses the event horizon, the point of no return. General relativity, in its description of black holes, predicts the existence of a singularity at their center, a point of infinite density and zero volume where the laws of physics as we know them break down. It's like dividing by zero in your calculator. The universe throws up its hands and says, "Error, does not compute." But this notion of a singularity, a point where space-time itself comes to an abrupt and messy end, sits uncomfortably with the probabilistic nature of quantum mechanics. Adding fuel to the fire is the black hole information paradox, a theoretical puzzle that has puzzled physicists for decades. Quantum mechanics, with its emphasis on the conservation of information, suggests that the information about the quantum state of matter falling into a black hole shouldn't simply disappear. But if nothing can escape a black hole, not even information, then where does it go? This paradox highlights the fundamental tension between general relativity and quantum mechanics. General relativity says, what goes into a black hole stays in a black hole, while quantum mechanics insists, information is never lost, something's gotta give. And resolving this paradox requires a deeper understanding of how gravity and quantum mechanics intertwine at the most fundamental level. Let's rewind to the Big Bang, where the universe was compressed into a point of unimaginable density and temperature. Gravity and quantum mechanics were locked in an intimate embrace. General relativity describes this evolution but stumbles at the singularity. Quantum mechanics offers a tantalizing possibility, the universe governed by quantum gravity. Quantum fluctuations could have provided the seeds for the universe's structure. The universe could have emerged from a quantum fluctuation, a cosmic burp from the vacuum. Section 5. A fragmented reality, the quest for a unified view. At the crossroads of physics, we have general relativity and quantum mechanics, each describing a different aspect of reality. It's like two jigsaw pieces that fit perfectly within their sections but leave a gaping hole in the middle. The missing piece is a theory of quantum gravity, reconciling smooth space-time with the quantum world. This quest has captivated physicists for decades, seeking a unified theory to explain the universe. A theory of quantum gravity could unlock black holes' secrets and reveal the universe's ultimate fate. The search for a unified theory is a journey into the unknown, driven by curiosity and a desire to understand our place in the cosmos. Strings of Hope, a symphony in 11 dimensions. Fasten your seatbelts, fellow physics fanatics. We're diving into string theory, a contender for the theory of everything. Imagine a universe where reality's building blocks are tiny, vibrating strings. These strings vibrate in 11 dimensions, creating a cosmic melody. Think of a garden hose viewed from a distance. It appears as a one-dimensional object, but zoom in, and you'll see a second dimension curled up and hidden. String theory suggests our 4 dimensions are just the tip of the cosmic iceberg. Hidden beneath are 7 additional dimensions, each influencing the strings. Imagine these strings vibrating at different frequencies, like a violin. Different vibrations create different particles and forces. One vibration might create an electron, another a quark, yet another a photon. It's a cosmic symphony, harmonizing the forces of nature. String theory offers a glimpse into a far stranger, interconnected universe. A universe where space-time is woven from string vibrations. A leap of imagination that could unlock the deepest secrets of the universe. Section 2. The world on a string vibrating our way to unification. So, how does this whole string theory thing actually work? How do these tiny, vibrating strands of energy manage to create the vast and complex universe we observe? Well, strap in, because it's time for a crash course in String Theory 101. Imagine a string, not as a static object, but as a dynamic entity, constantly vibrating, wriggling, and dancing in space-time. The way a string vibrates, its specific oscillation pattern determines its properties, much like the way a guitar string's vibration determines the note we hear. Now imagine these strings interacting with each other, colliding, merging, and splitting, like tiny energetic dancers on a cosmic stage. These interactions, governed by the laws of quantum mechanics, are what give rise to the forces we observe in nature. In string theory, there are no separate forces, just different manifestations of the same underlying stringy interactions. For example, the electromagnetic force, which governs the interactions between electrically charged particles, arises from the exchange of photons, the quanta of light. In string theory, photons are simply closed loops of string, vibrating in a particular way. When 2 electrically charged particles interact, they exchange these photon strings, much like 2 people playing catch with a frisbee. Similarly, the strong force, which binds quarks together to form protons and neutrons, arises from the exchange of gluons, another type of stringy excitation. The weak force, responsible for radioactive decay and even gravity itself, find their origins in the vibrations and interactions of these fundamental strings. It's a unified picture of the universe, where all forces and particles emerge from the same underlying stringy tapestry. But wait, there's more. Enter loop quantum gravity, a rival theory to string theory. It quantizes spacetime into discrete chunks like pixels on a screen. Imagine spacetime as a network of loops, woven like a cosmic tapestry. These loops are dynamic, defining spacetime's geometry and gravity. Now here's the catch. Both string theory and loop quantum gravity, for all their theoretical elegance, face a formidable challenge: the Planck scale. This unimaginably tiny scale, billions of times smaller than anything our most powerful particle accelerators can probe, is where the quantum nature of gravity is expected to reveal itself in all its glory. It's a realm where spacetime itself is thought to be a turbulent sea of quantum foam, where the very notions of distance and time become fuzzy and uncertain. Think of it like this. Imagine trying to study the intricate workings of a clock using only a sledgehammer. You might be able to smash the clock into its constituent parts, but you'd be hard-pressed to learn anything about how the gears, springs, and levers actually work together to tell time. Similarly, our current experimental tools are simply too blunt to probe the delicate dance of quantum gravity at the Planck scale. This experimental inaccessibility has made it incredibly difficult to test the predictions of string theory, loop quantum gravity, or any other theory that attempts to unify gravity and quantum mechanics. It's like having a map to a treasure island but no ship to sail there. We have the theoretical tools, the mathematical maps, but we lack the experimental vessels to navigate the treacherous waters of the Planck scale. So, where does that leave us? Stuck in a theoretical purgatory? Not necessarily. While the Planck scale may seem insurmountable, physicists are resourceful, constantly devising clever ways to circumvent limitations. Just as astronomers use distant stars as cosmic laboratories, physicists explore indirect ways to probe quantum gravity. One promising avenue is cosmology, the study of the universe as a whole. The early universe, moments after the Big Bang, was a hot, dense soup of energy where gravity and quantum mechanics intertwined. By studying the faint afterglow of the Big Bang, cosmologists search for subtle imprints, telltale signatures of quantum gravity. The search for a unified theory is a journey into the unknown, driven by human curiosity and our relentless pursuit of knowledge. The symphony of physics is still being written, and the search for the cosmic conductor continues. As we stand on the precipice of the unknown, peering into the depths of the cosmos, the universe in all its vastness and complexity thrives on mystery. It's a cosmic tapestry woven from threads of uncertainty. The search for a unified theory has been a long and winding road, yet the allure of the unknown continues to beckon us forward. It's a humbling thought, realizing that for all our scientific advancements, the universe still holds countless secrets close to its chest. The more we learn, the more we realize how much we don't know, and yet, it's this very realization that fuels the fires of scientific inquiry. The unknown isn't something to be feared, but rather embraced. It's in the unknown that we find the seeds of discovery. One of the most profound lessons from our exploration of the cosmos is that the universe is a deeply uncertain place. Uncertainty is baked into the very fabric of reality itself. Particles can be in multiple states at once, and observation influences the observed. Science isn't about clinging to dogma, but following evidence, even if it leads to uncertainty. The universe is far stranger and more wondrous than we imagined. Our understanding must be dynamic, always open to revision. Imagine the universe as a vast, uncharted ocean, and we are the intrepid explorers. Albert Einstein, the rock star of physics, left an indelible mark with his groundbreaking theories and insatiable curiosity. His quest for a unified theory, a single, elegant framework to explain the cosmos, inspired generations of physicists. Einstein's unfinished symphony reminds us that science is a journey, not a destination. The search for a unified theory is a testament to his enduring legacy. Each generation builds upon the work of those before, pushing the boundaries of knowledge. Einstein's dream unites minds across generations in a shared pursuit of understanding the universe. As we stand on the shoulders of giants like Einstein, gazing out at the cosmic horizon, we're reminded that the symphony of science is a never-ending performance, a grand and glorious composition that's constantly being written, revised, and reinterpreted. Each new discovery, each theoretical breakthrough, each experimental confirmation adds a new layer of complexity and beauty to the cosmic score, enriching our understanding of the universe and our place within it. The search for a unified theory, for a theory of everything, is just one movement in this grand symphony, a movement that's both challenging and exhilarating, filled with moments of profound insight and periods of frustrating impasse. But it's a movement that's essential to the overall composition, a vital thread in the cosmic tapestry that connects all of physics, from the smallest subatomic particles to the largest cosmic structures. The beauty of science lies in its ever-evolving nature, its willingness to embrace new ideas, to challenge old assumptions, and to constantly refine our understanding of the universe based on the evidence at hand. It's a process that's inherently collaborative, transcending disciplinary boundaries and uniting minds across cultures and generations in a shared pursuit of knowledge. So, let us embrace the unknown, celebrate the mysteries that still abound, and continue to explore the cosmos with open minds and a thirst for discovery. The symphony of science is far from over. In fact, it's just getting started. And who knows what breathtaking melodies, what mind-bending harmonies, what awe-inspiring crescendos await us as we continue to explore the universe and unravel its deepest secrets. The cosmic stage is set, the instruments are tuned, and the symphony of science plays on.